In this presentation, we're going to discuss how to calculate flexural stresses using the strain compatibility approach. By the end of this module, I want you to be able to apply given ACI 318 stress limits properly, calculate all required section properties, illustrate critical locations to check stress at different stages of a member's life, list stages of a member's life when stress must be checked, and finally, use the strain compatibility approach to approximate the elastic uncracked response. In the next few modules, we're going to focus on simply supported beams, but the concepts that we learn will be applicable to other members with other boundary conditions. More often than other members, we need to check the stresses and other limit states at various stages of the life of a pre-stressed member. So some of the times that we need to check are at pre-stress transfer, where we need to check the initial stresses in the concrete and reinforcement, under service loads, under long-term service, and under ultimate loads. Different codes will have different limit states. If you're working with bridges and AASHTO, there's several different limit states that you need to check, but the two that we would focus on are the AASHTO Service 3, where we're checking for our service level or service limit state and our stresses, and Strength 1, which would be the ultimate limit state, where we're checking our beam under ultimate loads. Different codes and specifications will have different stress limits for the various components of a pre-stressed concrete member. In ACI, we have a permissible stress limit for our pre-stressing tendons. And this permissible stress limit essentially ensures that we don't fracture the strand during the jacking and at transfer. So you can see the limits here. We have a limit during stressing at the jacking end. We need to keep the strand stress less than the least of these three values, and immediately after forced transfer. At the post-tensioning anchorage device and couplers, we need to keep the stress in the strand less than 0.7 times F sub PU. Typically with pre-tension strands, the stress that we have in the strand initially is going to be 75% of the ultimate strength of the strand, or 202.5 KSI. The permissible stress in the concrete depends on the time when we're checking stress, the location along the beam where we're checking for stress, and the type of stress that we have, whether it be tension or compression. Typically, during the initial stage, we need to check tension at the ends of the beam, we need to check compression at the ends of the beam, and we need to check tension at the top face of the beam at midspan. Typically, we also need to check our service stresses, and typically our tension at the bottom face of the beam will control. We can also check the compression at the top face, but that typically won't control. Typically our stresses, our service limit stresses will be controlled by the tension at the bottom of the beam. The allowable compression stresses in the end of the beam are there to prevent crushing or cracking of the young concrete and to prevent cracking in the future for the concrete. If you stress the concrete to greater than 0.7 or 0.8 times the release strength of the concrete, you're going to create these micro cracks in the concrete, and then later the concrete in those regions will be more likely to crack. So you can see different codes will have different limits, but typically if we're less than about 0.7 F prime CI, will prevent this microcracking. ACI 318 gives us two different compressive stress limits at release, depending on where we are in the beam. In the end region, we need to keep the stress less than 0.7 times F prime CI, the release strength of the concrete. And the rest of the beam, we need to keep it under 0.6 times F prime CI. It doesn't specify what is considered an end region, but typically the end region is about equal to the transfer length. So when we're checking our stresses at the transfer length, we can use this 0.7 F prime CI limit. ACI 318 also has tensile stress limits at release, and I summarize these here. And essentially what we're trying to do is we're trying to prevent cracking at the time of release in the end regions. One of the main advantages of pre-stressed concrete is we can keep our beam uncracked, so we want to make sure it doesn't crack when we first build it. So you can see that the limit again is differentiated between whether we're at the end of simply supported member or at another location here. If we're at the end of the member, we need to keep our tensile stress under 6 times the square root of F prime C, where F prime C is going to be in units of PSI. Other locations, our tensile limit goes down by a half, so we need to keep our tensile stress under 3 times the square root of F prime C. The tensile stress at release is one of the stress limit states that will often control our design. So we'll look at different ways that we can minimize these end region stresses. ACI 318 gives you an option if you do exceed the tensile limit stress at pre-stress transfer. They allow you to provide some non-pre-stressed steel in the region where cracking occurs to kind of restrain the cracking that occurs. So you can calculate the amount of steel that you would need using this equation here. But in general, if you can design your beam not to crack at the ends, you want to keep your beam uncracked. So any cracks will allow water and chlorides to get in there and start the corrosion process. So you want to try to keep your beam uncracked if possible. We also need to check our stresses at the final stage, or when our beam and structure is in service. At this point, we need to take off all of our pre-stress losses or consider all of our time effects, shrinkage, creep, and strand relaxation. And we need to apply all of our loads, so all of our dead loads and all of our live loads, all of our superimposed dead loads, all the loads on the structure would need to be considered at this point. Again, we have some compression and tension stress limits in ACI 318. For compression, we have 2 different limits depending on the load. We need to keep the stress or the compressive stress under 0.45 times F prime C for all of our sustained loads, our pre-stressing plus any other sustained loads, which would be the self-weight or superimposed dead loads. And then we need to keep the compressive stress limit or the compressive stress under 0.6 times F prime C for all of our total load, our pre-stress plus our total load. And this would include all of our live loads. ACI 318 has 3 different types of pre-stressed members depending on the tensile stresses that occur in the member. There are class U beams, which are uncracked beams, T, which are in the transition between cracked and uncracked, and then C, which is a cracked beam. The uncracked beam, we have a tensile limit of 7.5 times F prime C, or square root of F prime C. And this will ensure that our beam doesn't crack under the service loads. Some of the assumptions that we have here for class U beams, we're assuming that we have uncracked behavior, so we can use our gross section properties. The section properties that we use are gross section or transformed. The tensile stress limit, I already mentioned, 7.5 times the square root of F prime C. We don't need any crack control reinforcement, and we don't need any side skin reinforcement. These types of reinforcement are required if you have other types of pre-stressed members. Typically, we want to design our beam to be a class U uncracked beam. Keeping our beam uncracked is the main benefit of pre-stressing. It ensures that we have a durable product, so we want to make sure that we keep it uncracked. Next, we're going to talk about strain compatibility, which is one approach for calculating stresses in pre-stressed concrete members. The 2 main approaches here are that we'll talk about in this module and the next are strain compatibility, which we'll cover in this module, where we essentially find the strain at the centroid and the curvature in the section, and then we can use the strain and curvature to find the strains at any point in the cross-section depth, which we can use to find our stresses at any point in the cross-section depth. The other method used for calculating stresses is called the force in the tendon approach. And with this approach, we essentially assume that the pre-stressing is an applied force on our section. So this P sub I would be our pre-stressing force, and we just calculate our stresses based on our axial stresses P over A and our flexural stresses My over I, where the M for the pre-stressing would be the force from the pre-stressing times the eccentricity. So My over I. So we'll talk about force in the tendon approach in the next module, but this module will focus on the strain compatibility approach. With strain compatibility, we're going to assume that we have linear elastic material properties. And this is a valid assumption. As we saw with some of our previous modules, prestressed concrete has a large range where it stays linear elastic. So it's okay for us to assume linear elastic behavior, and at least initially. We need to check this and make sure that our steel, our pre-stressing, and our concrete remain linear elastic, but it's a reasonable initial assumption. To start, we can use our compatibility conditions, our constitutive relationships, and our equilibrium equations to solve for our stresses and strains in the section based on applied loads and pre-stressing. So to start, we can look at our compatibility conditions, and we can see that the strain at the concrete at any level is going to be related to the strain at the centroid and the curvature in the section, and the distance from the centroid of the section. The same is true with the steel, or any non-pre-stressed steel, and also true with the pre-stressing, except with our pre-stressing, we also need to include this locked-in strain differential, this delta epsilon P. With our stress-strain relationship, we can include any initial offsets to take into account shrinkage and our thermal effects. So we can include our epsilon C naught, epsilon S naught, and epsilon P naught for shrinkage and our thermal strains. And we can include these components in to offset our stress-strain relationship. So this just helps us relate our strain that causes stress in the concrete to the actual strain at that level where we're checking the stress. So then we can take this strain times the modulus of our different materials, because we are assuming linear elastic behavior for all of our materials. And we can find an equation here relating our stress to our strain at the centroid and the curvature in the section, and the distance from the centroid to whatever depth in the cross-section we're interested in finding our stress. We can do the same thing with our steel and our pre-stressing, remembering that we have this locked-in strain differential for our pre-stressing. As before, we can use our equilibrium equations, where our axial load is equal to essentially our stress times our area in our concrete, our steel, in our pre-stressing, keeping it as an integral to make it more general. We can do the same thing for our moment as we did before, where we're integrating again, but essentially we have our stress times our area times a lever arm component y. So we can make different substitutions, and the integration is not the cleanest, so we can simplify things by making a couple different definitions. The first is we'll define our N naught and M naught using these equations here. N naught is our decompression force. This is the force required to return our section to zero strain at the centroid. So our pre-stressing is going to deform the section and cause an initial strain at the centroid. So this decompression force is the force required to counteract that initial strain at the centroid. The decompression moment here is the moment required to return the section to zero curvature. So the eccentricity of our pre-stressing is going to cause an initial curvature in the section. So this moment is essentially to overcome that that curvature that happens. So to take it back to zero curvature, we need to apply m naught here. And we can then use these decompression force and decompression moment to calculate the strain at the centroid and the curvature, which we'll do on the next couple slides. To simplify our calculations further, we will transform our steel and pre-stressing into equivalent areas of concrete using our modular ratios. These ratios are just, it's the stiffness of the steel divided by the stiffness of the concrete for the steel modular ratio. And for the pre-stressing modular ratio, we're taking the modulus of a pre-stressing divided by the modulus of our concrete. So we're transforming our steel and pre-stressing into equivalent concrete areas by the stiffness ratios. With this, then, we can calculate the transformed area just by taking our concrete area plus our modular ratio for steel times the area of steel plus the modular ratio for our pre-stressing times the area of pre-stressing. We can simplify things, which I do in these two equations, to get it into this form. A lot of times in pre-stressed concrete, we'll be given the gross section properties. So it is handy to have a gross in the equation rather than our concrete area. So here you can just see it's here n sub s minus 1 times a sub s and n sub p minus 1 times a sub p. And in this equation, we're essentially just taking one area of steel and one area of pre-stressing over here to our concrete area to give us the gross area. After we have the transformed area, the next thing that we would need to do is calculate the transformed centroid of our section. And we can do that using this equation here, where we're just going to sum up all of our area components times the distance from, in this case, the top to the centroid of that area, divided by the summation of all of our areas. Now that we have the transformed area and transformed centroid of the section, we can calculate the transform moment of inertia for the section. We'll use parallel axis theorem. So we have our transformed moment of inertia is going to be equal to the moment of inertia of each of our components plus the area of the component times the distance between the centroid of the overall transformed section and the centroid of that component squared. So we have one portion for our concrete areas, one portion for our steel areas, and one portion for our pre-stressed areas. We're going to assume that the moment of inertia of our steel itself and the pre-stressing itself is equal to 0. So you can see here for the steel and pre-stressing components, we only have an AD squared component and we don't have the I component. And then this is going to have a very minor effect on your overall transformed section properties. We can do the same thing that we did for our transformed area and use our gross section properties just to make it easier on ourselves when we're given the gross section properties by, again, using n minus 1 to times the steel area and n minus 1 times the pre-stressed area. So you can see here, this will be the equation that we will use moving forward. We can use the decompression force and the decompression moment with our transformed area and transformed moment of inertia to find the strain at the centroid and the curvature in the section. And then with that strain and curvature, we can calculate the strain at any point in the cross-section depth, and then we can use that strain to calculate our stresses. Note that we are assuming that we have linear elastic materials, so we need to make sure that we don't violate that condition when checking our stresses. On this slide, I give you the basic equation here to calculate our strain in our concrete at any level, and we can then use that strain to calculate the stress in the concrete at any level. Typically, we'll want to check the stress at the top and the bottom of our section. Those will be the largest compression and tensile stresses in the section. So those will be the ones that we want to check. And you'll see that we'll also typically check the stress in the pre-stressing throughout in some of our examples. Note that we can take into account creep and shrinkage and strand relaxation just by using our effective modulus for our concrete and effective modulus for our pre-stressing, and by including the shrinkage strain right here in this equation. Note that everything that I've talked about so far has been with bonded tendons or bonded strands, where the strand is bonded to the surrounding concrete, either via grout or via direct contact between the strand and the concrete. For unbonded tendons, it's a little more difficult of a problem. One conservative assumption is to assume that the strain in the pre-stressing is equal to the locked-in strain throughout the service life. And so we can use epsilon p equal to delta epsilon p throughout our calculations. We also need to make sure that we don't include any unbonded strands when we're calculating our transformed properties. So that would be the other main change in what we've talked about so far. At this point, you can stop this presentation and go to the accompanying video for example 1, where we'll find the stress strain condition corresponding to no axial load and an applied moment of 53 kip feet, which is approximately equal to the self-weight for this rectangular section. And you can see I give you some of the properties that you'll need in terms of material strength. So 5 KSI concrete, area of our pre-stressing, and our locked-in strain differential. Next, we're going to see how we can include or find stresses at different times. And I'll walk you through how we can find stresses at release and under our sustained loads and also under our live loads. The main difference is that we need to think about when the load's being applied and if the load is sustained or short-term in order to decide what concrete strength to use and what material properties to calculate. First, at release, it's a short-term load. It's not a sustained load, so we're not going to use the effective modulus, and we're not going to include our shrinkage strain. And at release, our concrete strength is only going to be equal to the release strength. So the modulus we can calculate using the release strength for our concrete. We can calculate our transformed our transformed area using our modulus at release, and also we can calculate the transformed moment of inertia, again using the modulus at release, and calculate our decompression force and decompression moment at release. We can also calculate our sustained loads, our long-term load effect. And for these, we can use the same equations, except we're going to use our long-term properties and our EC effective and EP effective. So here, we need to use these in our epsilon centroid and our curvature equations, and also we need to use these when calculating our long-term transformed area and long-term transformed moment of inertia. The other change here is we need to include the shrinkage strain into our decompression force and decompression moment. So we can include those here, and just note that shrinkage strain is compression. So compression, our sign convention for compression is negative. So we would plug in a negative number into these equations. We can then find the strain at the top and bottom and stress at top and bottom and strain and stress in our pre-stressing strands using the same relationships that we did before. The only difference, we need to remember that we use the modulus with our release strength for our concrete, and our effective modulus for both the concrete and the pre-stressing when finding our stresses. And we also need to remember in our long-term sustained loads that we need to take out the shrinkage strains right here in this equation. So again, remember your sign convention. Next, we can find our strains and stresses from all of our live loads. And to do this, we need to use our short-term properties. A live load is not a sustained load, so we'll use EC with our ultimate concrete strength and EP, and we can find our short-term transformed area and short-term transformed moment of inertia. And note that we already accounted for our pre-stressing effects with our long-term sustained loads, so we don't need to double count our pre-stressing. So here, when calculating the stresses and strains from our live loads, our decompression force and decompression moment are both equal to 0. When we have our strain at the centroid and our curvature, we can calculate our strains at the top and bottom of the section and stresses at the top and bottom of the section and our strand strain and strand stress using the same equations that we have on the previous slides. We can remember that our live load is going to cause compression at the top and tension in the bottom. So we just want to remember that our sign convention, we should end up with compression in the top and tension in the bottom of the section. Finally, to find our total stresses under our service loads, we can add together our long-term sustained, or our stresses from our long-term sustained loads with our stresses from our live loads or our short-term loads. So we can add these together to get the total stress in the top and bottom of the section and total stress in the pre-stressing. And these would be the values that we would check against our stress limits from our codes. At this point, you can pause this video again and go to the accompanying video for our example problem number 2. And in this example, we're going to look at how to find the stresses and strains corresponding to a sustained or no sustained axial load, but a sustained moment of 50 kip feet, and a live load axial load of 50 kips and a live load moment of 120 kip feet using strain compatibility. On the next few slides, we're going to be going through another example problem where we calculate the stresses in the T section shown here, the single T section, using the strain compatibility approach, the force in the tendon approach, and the layered section approach. This design and the next couple slides are based on an example from Bayrak and Dickerson from the University of Texas at Austin. The span and load conditions are shown on this slide. You can see that we have harped strands with a single harp point at midspan. So we'll have a different eccentricity at the end of the beam than we do at midspan. And we'll talk about harping in more detail throughout this class, but essentially we do this to minimize the stresses at the end region and maximize the effectiveness of our pre-stressing at midspan. You can see the length is 80 feet, and we're given our self-weight, our superimposed dead load, and our live load on the section. So we'll remember that the self-weight and the superimposed dead load will be sustained loads, and the live load will be a short-term load when we're looking at our service stresses. We'll calculate the stresses at a few different locations along the length. So you can see here the location of the strand at a couple of different sections of interest. So at the end, at the transfer length, which is equal to 50 times the bar or the strand diameter, at 0.4 L, and at midspan. We'll check the stresses at about 40% of the length. When you have harp strands, often midspan won't be critical. Sometimes it'll be a short distance away from midspan, so that's why we'll check 0.4 L here. You can see here the gross section properties for the single T, and these are given. The material properties for our concrete and our pre-stressing are shown on this slide. So we have our concrete release strength, so our release compressive strength, and our modulus, just using our ACI equation and dividing by 1,000 to get it into KSI. And then our ultimate strength of 5 KSI. And then again, we can use the ACI equation to calculate the stiffness of our concrete. We're also given our pre-stressing strand properties. So we have 270 KSI strands. Our stiffness we'll assume to be 29,000 KSI. And we assume that we have an initial pre-stressing of 200 KSI, which gives us a locked-in strain differential of 6.9 times 10 to the negative third. We're going to calculate the stresses at several different points along the beam's length and at several different times in the life of the beam. And at each point, we will first calculate the decompression force and moment. Then we'll use that to determine the strain at the centroid and the curvature of the section. And then we can use that strain and curvature to find our stresses. We'll also calculate our deflections at the end using a moment area theorem with our curvature diagram. So that'll be provided at the end of this example. We need some of our long-term material properties because we're going to include the effects of our shrinkage strain and our creep and our effective modulus for our pre-stressing, which takes into account strain relaxation. So you can see here the volume to surface area ratio, relative humidity and loading age, and we can use these to calculate the shrinkage strain and creep coefficients. I'm giving them to you here to kind of shorten the example, but you could calculate these using any procedures for shrinkage and creep that you want. And then we can use our creep coefficient to calculate our effective modulus here, just by taking our modulus divided by 1 plus our creep coefficient. The effective modulus for our pre-stressing strand takes into account strand relaxation, and this is given in this problem. So it's given as 28,420 KSI. We'll need our transform section properties, and we'll need them at several different times in several different locations. So we need the transform section properties at release, and we'll find them at midspan, at 40% of the length, and at the transfer length. Note that we need to find them at different locations in this problem because we have harped strands. So the centroid of the strand is changing along the length of the beam. And because the location of the strand is changing, so will the transformed section properties. So that's why we find them at 3 different locations. Again, using the equations and procedures that we did earlier in class and in other examples, we can find the short-term transform section properties at our 3 locations and our long-term transform section properties at our 3 locations. We can now find our decompression force and moment, and we'll use the same equations that we did earlier in class and we looked at in other examples. So I just provide them again for you here on this slide. We can use the same equations that we did earlier in class to find the strain at the centroid and curvature, and then we can use that strain at the centroid and curvature to find the strain at any level of our section, and then that strain to find our stress in the concrete. So I'm going to go through it quick again because we went over this already earlier in class. We can also use the same equations that we went over earlier in the presentation to find the strain in the pre-stressing and stress in the pre-stressing, making sure that we include the strain differential in our equation here for pre-stressing strain. So the first point that we're going to find is our stresses at release. And to do this, we'll need to find our decompression force and moment at release. So here we have our decompression force at release. So we use our EP effective, our locked-in strain differential in the area of our pre-stressing to find the decompression force here equal to 428.4 kips. We can find our decompression moment here at release. And this is just our decompression force. So those 3 terms times this lever arm distance, which is the distance between the centroid of our transformed centroid and the centroid of our pre-stressing to give us a decompression moment here of 8,859 kip inches. The values on the previous slide were for our decompression force and moment at midspan, but we can also find we also need to find our decompression force and moment at 40% length and at transfer length, the three locations where we'll be calculating our stresses. We can use our transformed section properties at release with our modulus of elasticity at release and the decompression force and moment at release to find the strain at the centroid and curvature in the section, which I show you here. So we can find the strain at the centroid equal to negative 0.217 times 10 to the negative third. So this is strain and compression. And our curvature here, negative 12.089 times 10 to the negative 6 radians per inch. So we can use the equations from earlier to calculate the strain at the top fiber and strain at the bottom fiber in our section. And we can remember in terms of signs, our negative curvature is going to decrease our compression at the top fiber and increase compression at the bottom fiber. So when we calculate this here, our final strain you can see is less than the strain at the centroid. So this makes sense with the signs. We're decreasing our compression or adding tension at the top because of our curvature. And bottom fiber, we have a higher strain than we do at the centroid. So again, that makes sense with our negative curvature value here. So you can see just kind of how I had the sign set up, but you can check this conceptually at the end to make sure that you have the right signs. We can then take these strain values times the modulus at release to find the stress at the top and bottom fiber at release. And negative here is compression. So we have negative 0.3 KSI at the top fiber and negative 1.766 KSI at the bottom fiber. We can then check these values against our stress limits from the code. We can also calculate the strain in our pre-stressing strand using our equation from earlier and take that times the modulus in our pre-stressing to find the stress in the pre-stressing. Note that this stress in the pre-stressing is after all the elastic shortening has already occurred. So we don't need to take off any losses or anything like that when we're using the strain compatibility approach. On the previous few slides, we found the stresses at midspan, but we can do the same thing at 40% length and transfer length, which I'm showing you in this table. Next, we're going to find our stresses from our sustained loads. And to do this, we need to find our decompression force and decompression moment for long term. To do this, we'll use these equations from earlier in class and plugging in all of our values, making sure that we use the effective modulus for our pre-stressing, the effective modulus for our concrete, and in the equations, our shrinkage strain is compression, so we'll input it as a negative value. We can find the decompression force and decompression moment shown here. We can do the same thing for our decompression force and decompression moment at 40% length and transfer length, which I'm showing here in this table. Now we can use the moment from all of our sustained loads, which includes our self-weight and our superimposed dead load. And we can use this with our long-term transform section properties and effective modulus and our long-term decompression force and decompression moment to find the strain at the centroid and the curvature in the section. So you can see those values here. We can then use the strain at the centroid with our curvature value and the distance between the long-term transformed centroid and the top fiber or bottom fiber to calculate our strain at the top and bottom. You can see again, because of our signs, we have negative curvature, so we would expect a smaller compressive strain at the top and a larger compressive strain at the bottom, which is the case here. So we know that our signs in these equations are correct. We can find the stress at top and bottom by taking the strain minus our shrinkage strain times our effective modulus, and that gives us our stress. And we can find then our stress in the top fiber and stress in the bottom fiber due to all of our sustained loads. You can see these are both compressive stresses, so we can check these against the ACI limits. We can do the same thing with our pre-stressing strands to calculate the strain in the pre-stressing, making sure we include that locked-in strain differential, and then take this strain times the effective modulus for our pre-stressing, which takes into account strand relaxation, which will give us the stress in the strand of 161.9 KSI. We can find the stresses from live loads using the equations from earlier in class. We would first need to find the live load moment. And then with live loads, we're already accounting for the effects of pre-stressing with our sustained loads. So our decompression force and decompression moment are going to be equal to 0. So we can find the curvature just by taking our live load moment minus 0 divided by our short-term modulus for our concrete using the 28-day strength times our I-transformed short-term to get the curvature in the section. We can then use our equations from earlier to also find the strain at top and bottom fiber of our section. So here you can see the strain at the centroid is equal to 0 because we don't have any pre-stressing, and then our curvature is positive. So we would expect compression in the top and tension in the bottom. So it checks conceptually with our signs. And we can take the strain then times our modulus to get the stress in the top fiber and stress in the bottom fiber from our applied live loads. We can also calculate the strain at the level of the pre-stressing, so the strain in the pre-stressing using the same equation from earlier, except note that we don't include the locked-in strain differential here because, again, we already took into account the effects of the pre-stressing in our sustained load calculations. So we can calculate then the additional stress in the pre-stressing due to our live loads here by just taking the strain in the pre-stressing times the modulus, which gives us a total stress of 7.7 KSI. Our final step here is to add our stresses from our sustained loads to the stresses from our live loads. And we'll do that at the top fiber, at the bottom fiber, and at the level of our strands. And this will give us the stresses shown here. So we have a top fiber stress of 1.045 KSI, a bottom fiber stress of 0.428 KSI tension, which we can compare to the tension limit here. So we're below the tension limit at midspan. And then we can see our strand stress, our total strand stress at this point of 169.6 KSI. The calculations on the previous slides were for midspan, but we can do the same thing for our 40% length and transfer length locations. So you can see those values are all summarized in this table. And here summarized again are all of our stresses due to our live loads at the top and bottom fiber and at the location of the pre-stressing at 40% and transfer length. Finally, we can see the total stress at the top and bottom fiber and the total stress in the pre-stressing at midspan, at 40% length, and at the transfer length. due to all of our sustained loads and our live loads. You can see at midspan we check all of our stresses all check. We're below our tension limit at the bottom fiber, but at 40% length, because of our harp strands and the strand eccentricity decreasing along the length, the bottom fiber tension actually is above the tension limits, the 7.5 times the square root of F prime C tension limit. So actually this design doesn't check. So this just shows the importance of checking your stresses along the entire length of your beam. In the next section, we're going to look at composite versus non-composite sections. Precast pre-stressed sections will often have a cast-in-place deck or topping that's placed when the bridge or building is being constructed. We can use strain compatibility also to calculate the stresses in a composite section, but we'll need to understand when to use what section properties. Here are some examples of some composite sections that you may run into for bridge construction, like a bulb T girder with a cast-in-place deck, or building construction, like a double T beam with a 2-inch cast-in-place topping. For composite structures, there will be different types of loads and times when the stresses are found, and we'll need to use different section properties, either non-composite or composite, short-term or long-term, depending on what types of loads are being applied and whether they're applied to the non-composite or composite section. Here I just give a couple examples. So at release or transfer, we may have a self-weight and pre-stress loading, and these will be applied to the non-composite section, and they'll be short-term loads. When we're at erection or time of construction, we'll have the deck or topping that'll be applied to the non-composite section, and that'll be a short-term load, but then we'll have a sustained load on the non-composite section for our self-weight and pre-stressing. When we get to service, our sustained loads will be the self-weight and pre-stressing, the deck and topping, and those are all going to be on the non-composite section. And then we'll have the live loads, which are applied after the section becomes composite. So those will be applied to our composite section, short term. And then we may have other superimposed dead loads that are applied after composite behavior starts. So those would be on sustained loads on the composite section. For this class and for simplicity, we're only going to look at essentially at release and service, and we won't include any sustained loads to the composite section. We'll start by talking about our different section properties. These can include the short and long-term non-composite transform section, and the non-composite transform section will be used to resist any loads that are applied before the beam becomes composite with the deck. So this includes the self-weight and pre-stressing, and it also includes the weight of the deck or topping itself. The next set of section properties that we may need to find are the short and long-term composite transform section properties. And we'll use these to resist any loads that are applied after the beam becomes composite with the deck. So this includes the live load and also any superimposed dead loads that are applied after composite action starts. So you can see here I just highlight whether we'll need the non-composite or composite section properties. To find these properties, we'll need several different modular ratios. We'll need to still transform our steel, our pre-stressing steel, into an equivalent concrete area. And for that, we'll need our modular ratio at release, our modular ratio due to our sustained loads, where we use our effective modulus for our pre-stressing in concrete, and then also our short-term modular ratio, which is just here the pre-stressing to our modulus, our 28A strength modulus. So modulus at release, again, we're using the release strength for our concrete. We also, for composite sections, we also need to transform our cast-in-place topping or deck concrete into an equivalent girder concrete. And we can do that short-term and long-term. So here, this is just the ratio of our deck concrete stiffness to our girder concrete stiffness. Typically, our deck is going to be a lower strength concrete, so this value will be less than 1. Our non-composite section properties, we can find the same way that we've found our different transform section properties earlier in the class. So I'm not going to repeat those here. But again, we'll use the non-composite section properties to resist any loads that are applied to the non-composite section. And this will typically be the self-weight of the beam itself, and then the weight of the topping or deck. We can find the composite section properties using the equations on the next couple slides. The first thing that we need to do is we need to find our different deck properties. We can find our composite section height by adding our beam height plus our deck thickness. We can find our deck area and moment of inertia just by taking the thickness times the width of the deck and using our BH cubed over 12 equation for the deck here, remembering that our thickness is our H component. And then we can find the centroid of the deck from the bottom by taking the beam height H plus half of the topping thickness. We'll also need our different modular ratios, so I'm showing you 2 that we'll need here if we're finding our short-term section properties. So our short-term modular ratio transforming our pre-stressing, and our short-term modular ratio transforming our deck concrete. We can find our transformed section properties using the same type of the same base equations that we did earlier in class. The only difference is we'll have an additional component here, which is our transformed deck area or deck components. So here are our transformed composite area. It's just our gross area plus n minus 1 times our pre-stressing plus n for our deck times the deck area. We can do the similar thing as before for our transformed centroid. Here I'm finding it from the bottom of the section. So we have our gross area times the centroid of the gross section from the bottom. N minus 1 for our pre-stressing times the area of pre-stressing times YP, the distance from the bottom to the centroid of the pre-stressing. And then the N for our deck times the area of our deck times the distance between the bottom and the centroid of the deck. And then we divide all that by our transformed area. We can use these equations here then to find the transformed centroid, the distance to the top of the deck, and the distance from the centroid to the top of the beam. We'll need to find the stress at the top of the deck and the top of the beam, so both of these distances are important for us. Finally, we can find the transform moment of inertia. We had the same few components as before, our I for our I gross, our AD squared component for our gross area, our AD squared component for our pre-stressing area, and now we have 2 additional components for our deck, our N times our I for our deck, and then N times A for our deck times the D squared component for our deck. And that'll give us our composite transformed moment of inertia. Next, we're going to talk about how we can calculate stresses for our composite and non-composite section. At transfer release, we're only going to have our non-composite section, so we only need to find the stress at the bottom fiber and stress at the top fiber for our precast beam, our non-composite section. And we'll do this using the same procedure that we did earlier in the class. To find our stresses from all of our service loads, we'll need to find the stresses at the top and bottom of our precast section from our self-weight and the deck topping. These will all be sustained stresses because these are sustained loads. And then we add these to the stresses from our live loads, where here these loads are applied to our composite section. So we're going to have a stress in the top of the deck and the bottom of the beam. And when we add these together, we'll get our total stresses, which you can see we'll have a stress here at the deck that decreases and then increases here for the stress at the top of the beam, the precast beam, and then coming down to the stress at the bottom fiber. So this is how we'll combine the stresses due to our sustained loads with the stresses from our live loads on our non-composite and composite section. The stresses on in our section from our live loads that are applied to the composite section can be found using the same type of equations that we did before. The only difference here is that we'll use the composite transformed area and the composite transformed moment of inertia here to find our centroid, or strain at the centroid and curvature in the section. And then we can use this strain at the centroid and curvature with the equations that we used before to find the concrete strain at the top of the deck, at the top of the beam, and at the bottom of the beam, or the bottom of the composite section. And then we can use these strains times the modulus in our concrete to find the stress at the same levels. And then we can also find the strain and the stress in our pre-stressing. Here for our composite section, we're finding our stresses due to the live loads. So we've already included the pre-stressing effects in with our sustained loads on our non-composite section. So we don't need to include the locked-in strain differential here. So this is similar to what we did for just our non-composite section earlier in the lecture. And that brings us now to example number 3. So you can exit this video now and go to the accompanying video for example 3. In this example, we're going to calculate the stresses at service for the double T section shown here, which has a 2-inch composite cast-in-place topping. It's a double T, so we have the gross section properties, and I also give us all of our material properties, including our shrinkage strain and creep coefficient, and the relaxation effects, so the effective modulus for our pre-stressing. That concludes this presentation on finding stresses using the strain compatibility approach.